Hello, everyone. Welcome back to a Psychics podcast. And today we have the pleasure to host an episode together with Ricardo Rocha that accepted to be here. Thanks very much. And yeah, for a few people that doesn't know you, please introduce yourself and what you are working and where.
Yeah, absolutely. Thanks a lot for the invitation. It's a pleasure. My name is Ricardo. I'm a computing engineer at CERN. I currently lead the teams doing cloud native and machine learning platforms here at CERN in CERN IT. I've been at CERN for a long time. I actually started as a student a long time ago working on what's called the grid computing infrastructure before the cloud days, where we actually had to develop all the components ourselves. Things have changed quite a bit, so we transitioned to much more collaborate with large communities for computing infrastructures outside CERN, and this is where I also have a few roles in this community. So I'm very involved in the Cloud Native Computing Foundation. So I got CERN to join the foundation some five years ago now, and we are very present. We are end users, and we joined with the purpose of meeting other end users with similar use cases, and also trying to improve our own infrastructures and make them more sustainable. So, as part of that, I'm also joined the technical oversight committee in the CNCF. I'm happy to talk about that as well, and something called the end user technical advisory board as well. But it's basically making sure that the community keeps working. Yeah.
Yeah, a lot of stuff there. So
Yeah.
one of my first question is, okay, we are talking, and I agree that recently science, data science, cloud native are converging somehow, right? In many topics. I would say almost every topic. So what's your take on that? I mean, what are you seeing more at the infrastructure level, converging faster, or at the framework level? What do you think?
Yeah, so that's a good question. We do see a convergence on the infrastructure in terms of how things are managed. The the amount of data that has come in the last few years, but above all, the possibility to get access to large amounts of computing, especially with the public cloud providers, allows anyone to be handling kind of big data, like we used to call it. This has made data science in general a lot more interesting for many companies that before had little interest because basically they couldn't access the computing power. They didn't have the resources to build data centers, but it kind of became easier. I think the convergence in this area is happening. I think there is a sort of a split between the traditional data science that does more uh, what we'd call like classic scientific computing. Even not even GPU based is still using traditional methods, and the machine learning communities, which really have a very specific set of frameworks, have very specific requirements for the hardware, and we see especially with Gen AI the needs for like very large models, things like this. This is really a split we see between the two communities, and this has an impact on the hardware as well. Because if you ask someone doing classic scientific computing with GPUs, they will want lots of cores, lots of CUDA cores, and very performant floating point precision, things like FP32 and higher. While in the machine learning, we see the other tendency, which is to go to lower precision. So I think those are kind of still negotiating on how to share resources and environments.
Yeah, right. It's a a big change of paradigm, if you
Yeah,
want. Yeah, and so you mentioned data and big data. So just to set the scene for everyone, which kind of environment you are moving and which kind of science you are trying to facilitate.
all right. Yeah. So for sure. So I'm guessing everyone kind of knows CERN, but our main experiment is called Large Hadron Collider, which is a 27-kilometer particle accelerator where we collide beams of protons. And we have 4 large experiments located 100 meters in the ground. And the result of these experiments is really a lot of data. So when we do the collisions, each of these detectors acts like a gigantic camera, doing something like 40 million pictures per second, or what we would call pictures. Yeah, exactly. And this, the result of this is really a lot of data. So, for example, a detector like the Atlas detector will generate something like 1 petabyte of data per second, which is, of course, something we cannot handle. So what they do is they have what they call triggers, which are filters that then will do a very fast selection of these events. And then this data will be reduced to something like 10 gigabytes a second, which is something we can then store here in our data centers. And we have 2 data centers on site. And from that data, we then do what we call reconstruction of the events. And for that, we need a lot of computing power. So numbers-wise, we're talking around 70 to 100 petabytes of data per year. We already store more than 1 exabyte. And then computing power on premises, we have something like 400,000 cores, CPU cores. But actually, this is not enough. So we have this grid computing infrastructure, which is a network of 160, 170 centers around the world that contributes also some capacity, which give us in total something like 1 million CPU cores. And this is really the traditional way of doing scientific computing. It's not the GPU machine learning part, which is picking up as well.
Yeah, right. So for whoever is following the channel, we talk very often about the pipelines. These are very big and complex pipelines at any level. So yeah, and more focus on doing, if you wish, high throughput, right? So
Exactly. So that's a very good
get,
point, because this is not the scientific computing that you will hear often elsewhere, which is more high performance computing with things like MPI jobs, requirements for low latency connectivity. What we do is really what we call high throughput computing, which is a lot of independent jobs. So we will have hundreds of thousands of jobs running on this infrastructure, but they are really totally independent. So they can land in different parts of the world, and as long as the data is local, they can run.
yeah, very cool. Thanks. So for who is following live, if you have any question at any time, just drop a message. I can read it for you. And while people are taking courage to do questions, I want to focus a bit more to the tech and cloud native part, if you want. So you mentioned before a lot of interactions and a relationship with the Cloud Native Foundation. So yeah, can you? And I also love the fact that the end user community and research and the user community is talking to each other and is trying to coordinate the efforts. So yeah, please tell us more.
Yeah, so I can talk a little bit about the history of our journey as well. So we actually started by looking at containers, like a lot of people back in 2015, something like that. People started getting more interested in containers, and then once you start doing containers at scale or at some sort of scale, you have to start thinking about orchestration, and this is where Kubernetes was coming into the scene. For those that are, I would say, less young like me now, they remember that these were very unclear days. Docker was clearly the thing that everyone was talking about, but for orchestration, it was very unclear. We had Docker Swarm, we had Mesos, that was very popular because Twitter was running with it. And then we had Kubernetes, which was kind of the new thing, but it had a very strong backup from companies like Google, where it started. And then we actually started by offering our users all of them, and they could spawn clusters by choosing which one they want, because we weren't sure. But then as the Cloud Native Foundation was created and it started backing up Kubernetes at the start, it was the only project when it started. it became clear that there was something happening. So we started following it more closely. Then we saw things like Prometheus coming and many other projects that you can see in the Cloud Native Foundation webpage, graduated, incubating, different maturity levels. But it's been pretty amazing to see how the landscape has been augmenting. So CERN got interested originally from the scientific computing perspective, but actually it very quickly increased to be about running our services internally. So basically, most of our campus service these days run on cloud native environments. We offer our users the possibility to manage clusters, deploy their application, manage their applications, and that's a very important part of our infrastructure. And then, of course, the most exciting one is the scientific computing. Kubernetes, to be fair, was not designed from the start to run this kind of workloads. It was really for the microservices, service-to-service communication kind of thing. It did have things like the job that has been there from the very start, but the notion of a job in Kubernetes was more like a Hadoop or MapReduce kind of thing. It wasn't really like the jobs we're used to in HPC and HTC environments. So in the last, I would say, 6 years, our big role in the community has been to push for this kind of advanced primitives that we need for scientific computing. And we've presented this many times, but it's basically like advanced scheduling, support for detailed topology on the nodes for optimizing the resource usage, queuing, all these things, co-scheduling, gang scheduling. If you're doing HPC, of course, you know this. And just to finalize, I don't know how this works, but I will put a link here in the chat,
Okay.
which is we created this research and user group, which exists in the CNCF. And this is kind of the place where organizations like CERN hang out to discuss these subjects.
Yeah, this is cool because it's like translating or importing into the Kubernetes world the knowledge that you had
Yeah.
in various years of doing high throughput computing on the grid, if you wish. So, yeah, and I know, and I also see that in this direction there were an interesting talk at the last KubeCon in Salt Lake City, right? So, and there we start to go a bit more deeply in the technical details. So, if you had to summarize in 2 minutes what is going on the edge of this interaction of this development, what you are more enthusiastic about and what is coming. So then we are going to look at in the detail, but yeah, just introduce.
Yeah, absolutely. So it's been, I have to say, it's been a long journey. Scientific computing and cloud native were kind of not merging very fast, let's put it like this, in the first few years. But what the big trigger has been actually Gen AI. For the good and the bad, it actually, for the cloud native environment, it brought a ton of investment because to perform machine learning and large, especially to support large language models, you need these primitives that we are used to in HPC and HTC environments. So the things I'm really exciting is the scheduling part. So we had projects in the Cloud Native Foundation that were adding this functionality to Kubernetes, things like Volcano or Armada or others, but they were kind of separate projects. They were not designed to integrate deeply into Kubernetes, which meant that they do the job. They can do the advanced scheduling in terms of queues or co-scheduling, gang scheduling, priority preemption, and this kind of thing, or fair share. But they don't integrate very well with other components in Kubernetes, like the cluster autoscaler or the node runtime environments. They were not designed this level of detail. So the project I'm particularly excited about is a project called Q, which came out of SIG scheduling, which is the special interest group for scheduling inside Kubernetes. And this is really the one project that I think will bring the functional, or already brought most of the functionality we need, which is the ability to define queues, the ability to define priorities for the workloads, to gang scheduling, and then all the integration with the runtimes and the topology. So this is really the project I'm mostly excited about. Related to this, I think just below you showed one of the functionalities of Queue, which is very recent, which is called multi-queue. And this is the other part, which is quite interesting for us because Kubernetes was designed to be single cluster. Scheduling is one cluster, but there's a lot of interest to do multi-cluster, both on premises, but also to do hybrid deployments. And I think for batch-like workloads, it becomes quite easy to do it with multi-queue. For services, you had different options with service mesh providers, but for batch scheduling, I think queue and multi-queue is one of the key components looking forward.
Yeah, and I think in this regard, the batch functionalities can be useful for use cases that we know well, but how this compares to the AI and ML needs. So, what's your experience?
Yeah, so I think one of the motivations to really speed up the developments in Q has been the needs in Gen AI, and specifically for large language models, which do not easily fit in one single GPU, or for the extremely large ones that we start seeing now, even in a dual GPU or and people started looking at coordinating better these workloads because it makes a huge difference if you have the knowledge of the node layout and topology, and if you don't, if you can co-locate between GPUs, if you pay for a very expensive node with full interconnects between GPUs, you probably want to make use of them, otherwise it's kind of pointless. And then also for internode, for the really large scale deployments for machine learning, people are deploying things like InfiniBand for low latency interconnects, which is something that HPC supercomputers have been doing for decades. And this suddenly became a thing also for machine learning. So that's why I think this has been the moment where the interest and the hype on Gen AI kind of kicked the integration with cloud native. And the reason for that is that you could imagine that people would go somewhere else completely and just use totally different platforms. But the reality is that there has been so much investment in cloud native in the last 10 years, specifically from public cloud providers, also offering these APIs and other products and vendors offering the management of the infrastructure via these APIs, that it really makes sense to make an effort to also
Yeah.
run these workloads in the same place instead of like reinvesting everything from the start. And I think this is the main trigger.
And even if you move your frameworks, it doesn't mean that every framework is moving. So
Yeah.
you would have to re-implement. Yeah, right.
So you see things like one of the key points of Kubernetes is its extensibility. Like we always say, it's about container orchestration, but like if you look at it, it's much more. Like people are doing all sorts of thing management with Kubernetes because it has this idea of declarative APIs where you declare what you want, and then it has this notion of reconciliation that ensures that the backends actually apply what you're asking for. And then you can see that it's quite easy to integrate things like TensorFlow jobs or PyTorch jobs. You might be needing to distribute them, but then you write an operator that is capable of managing this. And this is like one of the main potentials, and that I think made it very attractive as well for ML.
Yeah, I always imagine this like it's not really an orchestrator. What the added value is exactly, yeah, as you said, this API layer where you can orchestrate states, basically, not any kind of problem you can define in that way. Then there are other considerations that you should do, but in general, you can implement
And
everything.
it's something that for non uh, like IT or people that don't have to deal with infrastructure, it's kind of a bit scary at the start. But we've had examples of physicists, and we actually use it as an example internally also for our users, which is someone that came to the office with a Python script to run some TensorFlow workloads, and they were running in one box with one GPU, and they wanted to scale out and they didn't know how. So first step was to containerize, and we just helped them out. And then we could run in one box with one container. And then we try to go from there to some sort of MPI like workload where you need knowledge of SSH keys and all of this. And we could do it with a couple of machines. But when you go to like 10, 20, 50 machines, managing this becomes a complete nightmare. So then we looked into tools like Kubeflow, which offer operators for exactly this, for distributing TensorFlow workloads or MPI workloads. And then you show the user again, like, here's your YAML. There's like 50 lines of YAML. Do apply, and yeah, go for lunch, and it will be done when you come back. And this is where the things become really attractive, because it does the perfect separation from the user defining the workload and the infrastructure managers.
Yeah, awesome. And I think it's also from the user perspective, this is really another value, because you have at that point to concentrate only on your analysis, on your
Yeah.
actually on your job. So
Yeah, if you're
that's
a physicist at CERN, it's guaranteed that you did a lot of system administration during your PhD.
yeah.
Well, maybe now it's not necessarily the case, or not so much anymore.
So do you have? Can you make an example, or do you have? It was not prepared, so don't worry to say no.
Yeah.
The there is some visual, some example of what a user at CERN it's capable of accessing, and how to can manage pipelines or whatever it needs for, let's say, data science in general, but yeah, the very final user that has
Yeah.
to produce plots, if you wish.
Yeah, so we have, it's a big organization, so we have a lot of options. This is the main problem that users will have, is which service is the best for my workload. But taking what I manage as an example, the way it works, and we have different levels of support in each component right now, but I will talk more about the vision of what we want, which is a user will have a platform where they have a notebook, and this is the entry point. And they will iterate on a notebook. They will get a notebook maybe with CPUs or maybe one GPU, and they will iterate a bit. Usually we are quite aggressive in terms of like culling idle resources to give the GPUs back to the pool. And this is one of the main benefits of centralizing this kind of activities, that you're not dedicating GPUs. You're giving leases of GPUs, and you're taking them back when things are idle. So from a notebook, a user will usually go to some sort of pipeline that will be usually either a training job, or for the cases where they already had some models, they will do some hyperparameter optimization, for example, for machine learning. So this will be step two, and the backend for these resources can actually be multiple things. So traditionally, this is an HT Condor farm, which is pure batch, HTC kind of thing. And in other environments, this is Kubernetes clusters with something like Kubeflow pipelines backing it up. And this is what we do today. It's with Kubeflow pipelines. And this will, for the hyperparameter tuning, they actually get the extra visualization in Kubeflow. So they get all the plots that show the convergence of the training. And then they also have access to things like tensor boards for more detailed analysis. And they can go back to, if it's a distributed training pipeline, they can also go back to the pipeline and, for example, try to see in one step, try to get more details, like, for example, launching a notebook from that particular step to do some additional investigation. This is
And
incredibly dependent on things like the storage system that is being used, but it's possible.
Yeah, and they are also capable of storing their models, right? So
Exactly.
they,
So the final step in all of this is that then the artifacts are stored in our own internal storage systems. For models, it's usually S3, and we are still not completely settled on the model management tools, but it's very likely something like MLflow to have the versioning and the model tracking. Uh, one thing that I will highlight, which is what we are working on today, these days, which is the actual resources where you're running will be usually on premises, but we have ways to integrate external resources, and this is where things get really exciting because you can go for spike for bursting to external resources, and this can be public cloud providers. And one very interesting topic is integrating directly with HPC centers, still with this cloud native platform. And this is really the dream: is that we get one single pane, control plane for all on premises and hybrid, be it public cloud or HPC.
yeah, and also in that there is a similarity with probably Gen AI development or something like that, because you might need an H100 for 2 hours, and
Yeah,
then you want to shut it down. So yeah, I suppose, as you mentioned before, it's in bad or in the good things. Gen AI is pushing a lot on
yeah.
all our.
So I I think that's in terms of platforms, that's definitely true. I think this is the part where Gen AI is also bringing bad things because the hype is so big right now that the idea of having an H100 for 2 hours and having them on demand is basically, I don't know, it's basically impossible. If you're trying to get this kind of resources on public clouds these days, you have to reserve in advance, and there's very little capacity that is available on demand. But the expectation is this will last for a bit, and then things will calm down, and we go back to the traditional public cloud model of on-demand resources, and not making kind of reserved capacity out of public clouds as well, which is not our main goal. Yeah,
Yeah. Uh, and by the way, you also have GPUs at the HPC centers, as you mentioned
exactly.
before. So
So
that,
those are that's one of the big breakthroughs that we might get during next year, I hope, which is to simplify the access to HPC resources so that people can do like what we were saying before, like a declarative API, declarative YAML, and some sort of magic on the back without them having to know details of where to log into it, the HPC center, how to push the data, and have to know a lot of the details of. Although most users of HPC are used to this, the machine learning scientists are not necessarily used to or willing to do it. So I think we have really a big opportunity to help them out here.
yeah, yeah, and people that are following the channel also knows that we are really looking into that for in different scenarios, both enterprise level and scientific level at INFN as well. And yeah, I see a lot of possibility and a lot of interesting
Yeah.
things coming up. So just let me go back by a step probably. So you mentioned the capability of your ML flow, or let's say on a pipeline, to be able to go and to another cluster basically, right?
Mhm.
And to run something on another cluster. Uh, this is possible in a nutshell, and which is the feature that you mentioned before in Q, how it works. So just zoom in a little bit
Yeah.
and see.
I'll do that, and I will also show what the problem, the things missing are still.
Yeah, cool.
And I will start by saying, if you are interested in this area, this is also the main advantage of this community. I will give you an example. We recently gave a presentation together with people from the Q team to kind of showcase what's possible in terms of multi-Q. And we did have chats during that week about what we would like to have in addition. And the result of that is that we are running a workshop here at CERN for one day in January, where the Q team comes here and we say what we need, and hopefully we get it kind of wrapped up in a few hours. So this is the potential of living in a community. Like, this would take a long time to do it by ourselves. But to add on the what this functionality is, so if you have ever used the job in Kubernetes, it's been there from the very start. So you probably have bumped into it. You have this notion of parallelism and completion, which is very similar to what MapReduce kind of workload would do, but it is like a deploy. It will try to run it. There's some failure policy and retrial policy, and then that's it. So what the Q team introduced is a couple of extensions to that notion, to that job API, which allow the job bit to be suspended. And when you do the suspending of a job, you allow the scheduler to then take a decision of where the job should be deployed. And this is what allows queues to exist. So you can have a job being submitted, it's actually suspended, added to a queue, and then there's a scheduler that will then decide where the job should go and make it run again, and then with the data of where it should go. Traditionally, will do this single cluster. It will just do the selection based on the cluster queues and the different nodes available. What multi-queue adds is that you can have an admission check. How is it called? That is actually checking a new resource that is called a multi-queue cluster, which basically what it does, it creates the same job on all the clusters that comply with the requirements. So if you say this job goes to this cluster queue and this cluster queue is backed by all these multi-queue clusters, what Q will do is will create the same job resource on all those clusters that match and see which one replies saying, I can run this job. And you run Q on those target clusters as well. So when one answers, I can do it, then Q, the master queue, will tell it, okay, you run it, and then it cancels the other two. So this allows us to do multi-cluster scheduling without the traditional dual-level scheduling that things like Mesos, for example, support.
And is the first cluster responding that will be assigned, or there is some bid, some priority in the play to choose where?
So
Okay.
the only decision right now today, the only decision choice is on the capabilities. So if you say my cluster has this much has capabilities for this type of resource, for example, a GPU or a GPU of certain kind, or TPUs or CPUs of certain architecture, then all the valid clusters that comply with those, the queue will give it a go. And then it
All
will
right.
receive from the first one that says, I can do the job, which is a pretty simple way of doing it. But actually, for our use case, it fits the job quite well. Of course, if you want to have more advanced policies, you can do this. And this is where these admission checks that I mentioned can come in, because you
All
can
right.
just write your own and have a different policy of how the cluster should be selected. So instead of being just the silly or the simple anyone that can, you can also add your own logic saying prioritize this type of resource against the other ones because of whatever cost or something like that.
All right. Cool. So, do you have an example of what have been your tests for this? So, what are your clusters that you are
Yeah.
matching in your day-to-day life? Let's say.
Yeah, so the ones we have immediately is the H100 GPUs. So we try to get them anywhere we can, and it's basically all the cloud providers we can get a hold of, and we are trying to integrate also with HPC farms, and yeah. So basically, this is it, because the delivery times for buying new GPUs are quite long right now, so we can kind of bridge the needs while we buy new ones with this more opportunistic kind of resources. Then for the workloads, they are very much traditional deep learning workloads that need to scale out. We don't, for example, one thing we don't do currently though is to split jobs across multiple clusters. So jobs will be collocated in one cluster, which means, for example, if you need, I don't know, 100 GPUs to execute a job, that specific cluster needs to have the 100 GPUs. This is something that we would like to improve, but the notion of like connectivity and latency across clusters and across administrative domains is still not there for us to be able to make these decisions. So for now, we just collocate all the job.
And what about data? So how do you distribute in this? I imagine that you have this kind of spike request, but then data takes time to arrive, so you prestage in some way. Or, yeah.
So this is where we are a little bit privileged, or quite privileged. The first aspect there is that because we have this kind of distributed computing infrastructure for 20 years now, there are several frameworks that are able to replicate data to all these target destinations on request. So we can, for example, integrate this sort of scheduling decision with some sort of policy of copy the data first, but don't reserve the resources immediately, wait for the data to be there, and then scale up the resources to actually use them. Again, this is in a world where public cloud is actually on demand, which is not necessarily the case for H100s today. The second part that we are quite privileged is that we do have direct dedicated links to all these external resources. And these are usually 100 gigabit dedicated links, which makes it higher latency, but not that much higher because most of them are in Europe, or pretty much all of them, these public cloud providers that we use. But it does have a little bit of implication in latency. But in terms of throughput, it's not very different from running here in the center, because you don't get much more than 100 gig. Usually you will have 100 gig connectivity between nodes anyway.
All right. Cool. So just to be clear, this multi-cluster configuration is not something that you can run exclusively at CERN, right? It's generally available, and whoever can get the hands on it.
Absolutely. So the pointers I would do is the Q website. It's Q with a K. That's the one where you can find all the information. The work happens. So Q is not a separate component. It's a sub-project of Kubernetes itself. So it belongs to the Kubernetes community. It's not a separate community. And the other point I would put is that Q was actually developed out of a dedicated working group, which is called Working Group Batch inside Kubernetes, and they meet weekly. So if you have an interest in trying it out, an interest to report about your experience, or some feature request, all you have to do is join the meeting, put your item in the agenda, ask for help. And again, like before Gen AI, there used to be like 4 or 5 people in these meetings. Now, if you join these days, you will have 40. So things have exploded significantly. Yeah.
Yeah. So let's populate with more researchers then. So
Exactly.
yeah. Good suggestion, and I'll share the link to the working group later in the description. So don't worry. I think it might be time to wrap up. I don't know if you have anything else, Ricardo, about the setup, or one general question. How was the KubeCon?
Yes. So I can wrap up and then talk about KubeCon, but also talk about the community, the status, and where we're going, or I think we're going. So KubeCon was quite exciting. There were over 9,000 people there. The topic, there was a dedicated collocated event for cloud native AI, which will be repeated again in KubeCon London. Same is true for Kubeflow Summit. There will also be one. And these are the places where we are discussing most of this. I think
And call for papers are open.
for the
Yeah.
collocated events, you can
Yeah.
submit until December 4th. So
Yeah.
they are open for a couple of more days. For KubeCon, they closed last Sunday. The topics that I think are most interesting for the scientific computing communities right now that are happening in the Kubernetes area and that I'm really excited about. One is Q, but we talked extensively about it. The second one I'm really excited is something called DRA, which stands for Dynamic Resource Allocation. And this is something that will change significantly the usage of resources in Kubernetes. So if you are using a GPU today, let's say an NVIDIA GPU, you're definitely aware of the NVIDIA GPU operator if you're running Kubernetes. And then you will have the possibility of assigning a resource called nvidia.com/GPU. You can also partition the resources. So an H100 or an A100, you can do something called multi-instance GPU, and the operator supports this. You can expose this with specialized nvidia.com/GPU, and then like the type of sharing you want to use. There's sharing, time slicing, partitioning, all these things. The dynamic resource allocation tries to kind of abstract all of this so that you don't have vendor-specific ways of doing all this resource allocation. And where this gets really exciting is that right now, the version that exists, the implementations, mostly from NVIDIA, work a bit like before, but you can look further where people can come and say, I need a GPU with 10 gigabytes. And then the operator will actually partition this dynamically for you. And this is quite exciting. So you don't, as an infrastructure manager, you don't have to anticipate these things and pre-partition or pre-slice the resources so that you accommodate the workloads you think will come, but you leave this to the orchestrator again. And this will be a very important improvement. And it's not only for computing resources. The same will happen for things like networks. If you end up having jobs in nodes that need special connectivity or some special acceleration on the network, a DRA implementation of that specific resource will be able to do this for you dynamically without you having to think about it. This is very exciting. And it's currently in beta. So if you deploy Kubernetes 132, or it will be in beta in 132, Kubernetes 132, you can try this, give feedback. And if you're joining KubeCon London, you can definitely expect a lot of news there.
Yeah, cool. So we are approaching a period where you will have really a continuum of all your resources, and you can draw the minimum amount that you need and get it.
This is exactly the goal. We always talk about I don't know, in organizations like CERN, why aren't we going faster with the machine learning? And a lot of it is because we are not making very good use of the hardware resources because we are dedicating them, and it's very hard for people to get access because we are not making a very good use of the resources we buy, and they are extremely expensive, so we cannot buy a lot. So this will be a game changer if we improve this.
All right. So yeah, very interesting. Thanks for the heads up. I think many. As soon as we have some time, we also try this feature. So
yeah,
thanks.
And if you need any help, like we hang out in the end user group for research.
Of course.
So anyone is more than welcome to join and help out as well.
All right. So yeah, I don't know if some people I see connected want to ask something. Otherwise, we wrap up and we can close. I suppose that they have already enough information to to digest. So, all right.
Cool.
I'll put all the links for everything we mentioned in the description. And as Ricardo said, yeah, please join and don't be shy. Propose request or report what you're doing. And thank you, Ricardo, for joining and
Thank you
for
for the
all this
invitation. It's been a pleasure.
latest
Yep.
latest news. And yeah, have a nice day, everyone.